Okay, so we have seen how to get richer models so far for regression, right? So we started off with just having features X, but then we pretty quickly saw that you could construct things like polynomial features. And then you still had a linear model, but you could represent sort of more complicated things because you'd augmented or lifted this feature space in some pre-specified way, right? So you had to know how you were going to do it. You could kind of do it arbitrarily. You could construct whatever features you wanted. Polynomials are kind of a very common one. And then the other way you saw this, that you could do this was with this idea of kernelizing things. And this also lets you get more complicated models. But in both of these cases, you had to decide ahead of time that you were going to use, for example, polynomial features or up to what order, or I mean, maybe you do cross-validation to pick the order, but you still had to decide that you were going to go with polynomial features, or you had to decide what kind of kernel you were going to use, like a polynomial kernel or a radial basis function kernel. And so these are kind of manual procedures. And so we're going to now get into neural networks, where one of the main benefits is that sometimes you can kind of create your own features. So you don't have to make these manual decisions, although that's a little bit of a bait and switch. And so you should remind me when we're done why that might be a little bit of a bait and switch. But just for one reason, that this isn't a bait and switch, but you need a lot of data in order to do that. And so, for example, in a lot of the problems I work on, we don't have these vast quantities of data. And so you can use these models, but they're actually not going to really outperform a lot of other models. But there are a whole set of problems out there for which you get state-of-the-art results with neural networks. And so, as you all know, these have become very popular. And we're not going to make it a big focus of the course, but it would be kind of crazy for you to go through an introduction to machine learning and not learn about them. So most of it will be in today's lecture. Depending on how the speed of other stuff goes, we might I might add something in towards the end on some more advanced topics there. Okay, so despite what the media says about AI and the brain and all this stuff, these are really just a composition of regression. And it turns out you get a lot of richness and complexity when you do that, and you also have to think very carefully about how you're going to do learning in these models. And so on the one hand, it's sort of a very simple idea, but getting it right took many decades before these things actually got into mainstream use and into industry. And so, but just as an example, what I mean by a composition of regressions is normally when we're talking about linear regression, well, we would only have one output layer, right? The regression label. Neural networks, we often generalize this, and often this is because it's classification where each of these is for a class. So you can, in these diagrams, if you're thinking regression, which we're going to start with, just think there's one output here. And normally you wouldn't have this sort of what we call in neural network lingo the hidden units, right? You would just take the x's, which are what we call the input units in neural networks, and you'd multiply them by a weight vector like this, and then you would get the outputs. And then you would check how your output is compared to the target you were seeking, right? But now we're introducing some more complexity where we're going to introduce these hidden units. And they're hidden because the thing they output, we can't check it against anything. Like, we don't have a ground truth here. It's just some intermediate computation. And then we take those intermediate computations, these hidden unit outputs, and we pipe them back into what is another regression here, right? And only then, at the sort of last layer, do you get the output. And that's the output that you can compare to the actual target signal y and compute gradients on a loss function that looks at both of these. And so this is a kind of little toy example where there's one layer of hidden units, and you may have seen other ones, and I'll show you some figures where these can become really crazy complex, like super, super deep, which means many, many layers, and generally they're also much wider. And right now, and so this sort of figure here, this schematic of how things are connected is referred to as the architecture of the neural network. And so for at least, we'll see how far we get today, but we're going to talk about what are called fully connected feed-forward networks today. Mostly, depending again where we get, but so what that means is feed-forward means that all the information flow is going forward, kind of like, right, you start down here, you compute these layers, and then from there you compute these, so that's the sense in which it's forward. There's no loops back, which you can get in other architectures, and it's fully connected because we assume that each of the hidden nodes is connected to all of the outputs, or similarly, each input is connected with a weight to all of the outputs. So there's no sparsity here, there's no structure, they're just fully connected. So that's sort of the really basics here. And I think that's all there is to say on this, but just to get you thinking about this and where the the interesting bits come from. So imagine here, I haven't specified what G and F are, right? So if this was if I looked at just this and this was our regular linear regression, this was the output, then F would just actually be the identity, right? It would be a linear model. So what if I had G linear and F linear? Then what would happen? Yep. It would be like you didn't have the hidden layer. So if all you do is connect layers together with linear, we're going to call these activation functions as the lingo of neural networks. If all you used were linear activation functions, then you'd have a composition of linear functions, which ultimately is a linear function. And you would actually gain nothing by having this depth. It would be as though you had just a linear regression model, actually. So typically these are non-linear. Sometimes you'll see a linear one at the end in regression, but generally, as you go through the network, these are very specifically non-linear in order to get rich, complex models that can capture all kinds of signal. So some of the choices that get used are shown here, sort of the mathematical form. So tan-H, sigmoid, which has a similar shape to tan-H. There's something called ReLU, and so what do these look like? And I'm going to get more into the pros and cons of these later on, just to give you an idea of like what are these functions as we're making progress. So you could have a linear threshold function like this, right? That's basically a sign function. So if you're below, if the linear additive sum is below some amount, you're a 0, and otherwise you're a 1. Or you could just have a linear function here. You could have a sigmoid or a hyperbolic tangent. These both asymptote, right? So they have a sort of linear portion, and then they don't go higher than 1, and they don't go lower than 0. So these are different choices. Classically, the sigmoid is the one that was used for actually decades. And a bit later in the lecture, we're going to find out about what some of these pros and cons and why that's actually not currently the one that's most frequently used. So I don't know if people know the full history, but so when I was in graduate school, there was a small contingent of people centered around Jeff Hinton who were working on neural networks, and they were honestly the laughingstock of the machine learning community, which is hard to imagine right now. People thought these would go nowhere. They'd already kind of died off once. And it's pretty amazing for me to have been there and now to see where things are. And in particular, so Jeff Hinton and Joshua and Jan, who actually worked with Jeff earlier in their careers, they worked on this stuff for decades and were kind of really laughed at to the point that they were sensitive. And of course, this year, you know that they just got the Turing Prize for this. And so sort of a testament to perseverance and vision and maybe obsession. I don't know. It's quite interesting. And of course, right, this has created a multi-million-dollar industry. So when I was in grad school, there was no money in this. No one was using this. We just did it because it was interesting, and there was actually not really any promise of a job other than maybe some obscure academic position like I have now after being at Microsoft for a long time. But of course, I like my job. But, and so just if you want to actually see what's going on here, right? So I was in grad school roughly in 2005, and you may have heard of the AI winters. So there's one before me, and that's when some other bad stuff kind of happened. And in this one, actually, it was not, as I said, very common. And then sort of just after I graduated, I went to Microsoft. It started to get very popular. That's when they really figured out how to train deeper neural networks. It's when Jeff went to Google and started working with them, and it really started to take off. And so you may not know, but one of the big machine learning conferences is called NeurIPS. It used to be called NIPS. And so this, can you see? It's a little small, but maybe you can make it out. So it's quite remarkable, and it's kind of fun to tell my colleagues in other areas about this. But so this is when they open. I don't actually understand the axis here, but this is basically the timeline of when they open the registration and how, as the days go by of open registration, how the enrollment increases. And so you can see that it was basically, similar patterns for a while. And then this one is 2017. It just sort of took off. And you may not know this, but right now, so when I was in grad school, this conference was maybe 500 or 700 people. The conference is now sort of capped at 8,000, and it sells out in about 15 minutes. And actually right now it's like a lottery system, basically. I think they've changed it to a lottery. It's just crazy, right? It's worse than trying to get a ticket to Burning. A different experience, mind you. So, okay, so why are these things so popular? They've been around for decades, so like what explains this kind of bizarre trend? I mean, well, partly that trend you just saw, that's because they started to work, and then the money followed, right? So then people follow. And so, as I said, these are kind of arbitrarily expressive, and we'll get into some intuition about why that is. So there's sort of what we call in machine learning, when we say high capacity, we mean that they're very expressive and they can capture almost any kind of signal. Of course, we know from the bias variance trade-off that that's not enough to do well, right? You could have a sort of infinitely rich or expressive model, but if you don't have enough data to fit it, you'll overfit and you won't get any generalization. But these have sort of arbitrarily high capacity because you can just make them deeper and wider, and this more or less increases their capacity. And then they're also composable, right? Like when we'll get a little bit, hopefully, into some of the other architectures, but you can do sort of neat things where you get little modules and you can just compose them together like Lego blocks. And then that composability of the architecture combined with the fact that you can automatically compute gradients, which we're going to talk about today, means that it's just like a really powerful, somehow plug and play. It's not quite, but it's getting there. And as I mentioned, there are some domains in which we have really state-of-the-art results now that just blew away benchmarks that existed for decades. But people, so for example, I work a lot in biology, and people use these all the time there, and there's often no evidence that they do any better than any other models, but they're very trendy, so people put them in there. So, right, so why did they become only popular, roughly 10 years ago when people have been chasing these forever? And so one thing is that they're starving for data. They need a vast amount of data, and often this analogy is made to like, well, how come babies can learn with just a few examples, and neural networks need, like millions and millions of examples that it's pointing to something wrong with the setup. And probably that something has to do with prior information, right? That you're not encoding. Like a baby is born with a brain, and the brain is affected by evolution, and in some sense, evolution is a memory of everything that humanity has seen, right? And if you don't give something similar to a neural network, then it's going to have to somehow gain that, it's going to need all that data that it's not otherwise sort of implicitly seen. And so people are thinking about this, and I mean, we're not going to talk about that, but it's just that for a long time there literally wasn't enough data to actually train these models such that you could see the really good results. And then the other reason was that there was this thing called sort of usually vanishing gradients, which is that when you tried to make them deeper, which is what normally people do to make them more expressive, and you try to do gradient descent, that even when you're sort of technically correctly computing the gradient, for reasons they would kind of go to zero and you couldn't train these things. And that was a really big bottleneck. And so people figured out how to get around that. And then the last thing was that you do see these multi-million-dollar models now, and they do take a lot of compute to train. And actually, so hardware improvements have also been responsible. And it's sort of the confluence of these three factors, something like roughly 10 years ago, that have made these things really popular from being a total laughingstock. Okay, so back to what these are. So we mentioned that, or I mentioned that they can be sort of arbitrarily expressive. And so just to give you a sense of that, so in fact, the actual sort of formal technical thing is that you only need one hidden layer in this. So remember back here, this was the hidden layer. So you often see things where you stack these and you have many hidden layers. So typically no one is using this with one hidden layer, and we'll get to that in a second, but sort of theoretically you need only one hidden layer. It might need to be arbitrarily wide, and with a nonlinear activation function, then you now have a universal function approximator. Similarly, actually, to the polynomial space, right? But if you can sort of visualize that here. So what this shows you is, imagine you're trying to approximate this regression curve that's in blue. And so how are you going to do that? You're going to do it with these nonlinearities that are parameterized. And the nonlinearity that's shown here is one of those activation functions I mentioned a few slides up. I didn't mention it. Okay, we'll get to it. But so I'll tell you more about it in a second. But it's a ReLU, which stands for rectified linear unit, and it just is basically max of 0 and z. And so what that means is that it's linear above 0, and then it's just 0 below. And so depending what you put in here, you can shift these around and change the slope. So each ReLU gives you something like this, where it moves around and the slope changes. And so you can imagine just essentially trying to put a whole bunch of little ReLUs here and add them all together to mimic what this red line looks like. And so actually it turns out, I mean, maybe when you go home you can spend more time looking at it if it's not obvious now, but if you basically add all of these simple little ReLUs together like this, then you get actually this blue curve. Sorry, the red curve that approximates it. And you can see it's approximation, right? So in particular, you see these pointy things, and that's from this little hard kink here, and the real curve doesn't have it, so it's not perfect, but if you went arbitrarily wide of each of these is essentially a hidden unit, right? And so the more of these you have, the wider a single hidden layer network you have. And with more and more of these, you can essentially make it less and less kinky and more smooth. And in the limit, it would be smooth. And so it's sort of intuitively for this reason that even with just one hidden layer, as long as you have non-linear activations, that you can approximate any curve quite well. Any questions so far? Okay. So if one hidden layer is enough, why is it that the whole world is using more than one hidden layer? Any guesses? It's actually completely not obvious, so I feel like if someone answered, it's because they read it somewhere or they took a class already. And to be fair, these are actually kind of almost open research questions. So much about neural networks are not understood. We use them as engineering tools, but in terms of like what they're actually doing, there's a lot of open questions. But the sort of sense that is emerging from the research community is that you may, well, and you can see from the last examples, you might need these really, really wide layers, and that uses a lot of parameters. And it turns out that when you have a deeper one, that you can actually get sort of the same capacity or expressiveness with fewer parameters. And somehow, the other thing that's sort of, this is really not super well understood, and there's many theories about it, is that when you do optimization of the parameters here, the optimization landscape changes because you have different parameters, a different structure, the loss function is different as a function of the parameters, and we don't quite know why, and there's many conjectures, but somehow when it's deeper, the optimization becomes easier. And what does that mean? So last lecture we talked about local minima and global minima, and I mentioned that actually in neural networks you don't necessarily want to get to the global optimum. It turns out that some really, typically in a large enough network, that's some weird part of the space that won't generalize well. And so something about the combination of how we set up architectures with the way we do stochastic gradient descent means that these deep neural networks just tend to work better in practice. So that's not a very satisfying answer, but that's, I think, the most we can give you right now. So, but overall, I just want to emphasize that we're basically in the same landscape we've been in through the whole lecture, right? Is we have paired data, and at the moment we're still talking about regression, but of course it can be used for classification. Yeah, so actually this says classification. Right now we're still talking regression in principle. And then you have a model class, and it just turns out that instead of, you know, a very specific linear model with a hand-coded set of features, instead you have this very complex composition of essentially regression functions coupled together with nonlinearities. And so that's this. And again, you're going to have to pick a loss function. And so frequently for regression, you'll see the same loss function we've seen before, which is squared error, which can emerge from assuming a Gaussian error assumption. And then you're again going to have a loss that you need to minimize, and you're going to sum it over all of your data points. So really, the whole, in terms of like, you know, backing away from like what is machine learning and what are the things we think about it, this is still the same thing. It's just that we have an extremely complex class of functions here. Okay, so how do we train these things? Typically, these are done with stochastic gradient descent, which of course we learned about it last time. And we talked a little bit about the step size, and we're not going to go too much into that. But like one of the popular ones, for example, is Adagrad. But if you Google like learning rate, or so step size is a synonym for learning rate. So if you were to Google this out of curiosity, you could find whole blogs written about all the different ways to do this. And some of them, like Adagrad, are backed by theoretical development, and some of them are a bit more of engineering hacks. And so this is actually kind of the messiness of modern day neural network research. Is it's like half, I don't know, a large proportion of it is kind of engineering hacks, which gives it a dirty name to the people who like to think rigorously and cleanly, like we sit in computer science departments. And then, but there is a bunch of coherent, rigorous stuff as well. But since these became so popular, people just jumped on the topic, and you can just install scikit-learn without knowing very much and just hack away, right? And sometimes these things work well. But the main point is that we're going to do stochastic gradient descent. And so the question might be, is like, you certainly didn't really, it's hard to imagine how you could programmatically compute gradients in these huge networks, right? And so that also historically was one of the challenges for neural networks and getting them to work, is how do you get the gradients over many layers? And so you may have heard this term backpropagation. And so backpropagation is basically a programmatic or automated way, if you will, to get gradients out of these kinds of neural networks. And so we're going to talk about that in this class and go through it. Any questions? Yep. Mm-hmm. So the capacity wouldn't be any different, right? You would still have a linear network. I mean, basically what happens is you're multiplying things together, so you might end up with like a W1 times a W2, but you could just replace those two parameters with a single parameter, right? Because it's just linear composed with linear. And your question is, so the capacity would be unchanged, but and we may not get to this because it's a more advanced topic, but it would perform differently if you got deeper. And the reason it would perform differently is that you have to be very careful with gradients, and the deeper things are, if you're not very careful with how you're doing it, the gradients can tend to vanish. And so even though you haven't bought yourself anything in terms of capacity, practically when you're running optimization, you may have difficulty and it may not optimize very well. So I would say if you're just composing linear layers, you gain nothing in capacity and you potentially lose something in optimization. Okay, so backpropagation it sounds sometimes like this fancy thing, but it's really just the name of an algorithm for efficiently and programmatically computing the gradients of a neural network objective function. And that's basically what we run. We get those gradients from this algorithm. Once we have the gradients, then we just plug them into what we learned last week, which is gradient descent or stochastic gradient descent. Okay, so let's carefully walk through this. And so you're gonna go through some of this in homework. So we're gonna start with the basics and work our way up. So everyone here should know the univariate chain rule, but just to get warmed up here, right? So we have f of x and x of t, and that's the standard chain rule. I don't think we need to spend too much time on that. But so now let's imagine that we have a univariate logistic least squares model. And so what that means is L is going to be the notation for our loss, Y are our data, and Y are the predictions, regression predictions, and T are the true predictions, right? So this is just a squared loss. We put a half there just because it makes the gradients look nice sometimes. This sigma here is a just general notation for a nonlinearity, or this activation function. And then this is so you still always see this sort of linear additive bit here. Here the offset is written. Sometimes we absorb that into the W, right? So usually you just see WX. And so in this case, you compute this, which is going to go into the nonlinearity, and now you get that, and then you compare only after through the nonlinearity to the target. And so the idea is, in this very simple example, this is basically like a one-layer neural network, I guess, and we want to compute the parameters with respect to W and with respect to B. Okay, so that looks pretty simple, right? And so what does that look like? I just keep the box up here so you can see for reference what everything is, although it's here, right? So that is the loss, and we're going to compute now with respect to W. So we just first pull out the half, nothing else tricky. I mean, there's nothing tricky here at all. And then we just apply the standard rules that you've seen. Take the 2 times the half, goes away, and now we got rid of the exponent. Then we take the derivative of the activated thing with respect to W. And which we're going to right, sigma prime, and then we take finally the last part of the chain rule, where we take the derivative of the very last bit inside there, so we're to w, and that this thing, of course, is just equal to x, right? So that's where this x comes from. This is the derivative of the nonlinearity, or the activation function, and then this is, it comes from that first bit. Okay, so far so good. Nothing you guys couldn't have done without this class. Similarly, if we wanted to get the derivative with respect to b, which is this offset, or bias it's sometimes called, so it's going to look the same, right? I don't need to go through, but basically, when you get to this stage here, you don't have anything next to the b, so you get nothing there. So it looks the same, but you don't have that next term. Okay, great. So those are derivatives, now we're done. Except this isn't really programmatic or automatic. This is like you sitting down in first year calculus and applying the chain rule. So that's not super useful. And so what we want to do is like shift our heads away from first year calculus and think about ourselves as computer scientists who have to program this, right? And so how are we going to do that? So we want to think of it in a more structured way. And in some sense, that's like the whole key to thinking about backpropagation. It's not to most easily do this by paper and pen. It's to do it in a sort of organized and structured way that you can then program that will be very easy to apply to almost any kind of model. And so you can think about, and it's sort of, well, it'll become more and more obvious what I mean, but so right, first of all, compute the loss, and so you kind of do this. I mean, here it looks simple, but you can imagine like I'm going to try and describe the principle here, but you start with this sort of thing in the very inside of the composition, and then you pipe it, so the z here now goes to this sort of next part, right? So there's a chaining here where I compute something here that depends on nothing. This line here depends on the previous layer, and this line here where I actually get the loss I want in turn depends on the previous layer. And so here there's just a few layers, but in general, when you're computing the loss through a large, deep neural network, you're going to get this sort of chaining effect, right? You're going to compute, push up, compute, push up, compute, push up. This is going to be called the forward pass of backpropagation. But so far, that's like computing the loss is not the hard part. And you could have all done that without the course, but I'm trying to sort of get you to see what these sort of principles and the structure is here. The trickier part, of course, is computing the derivative. And so in this case, right, we are just going to say compute the loss with respect to y, and then we're going to just compute all of them and now to get the loss with respect to z, I can just use the one above. So again, I'm going to get this sort of chaining effect where this guy uses that one, this guy uses that one, and also this guy uses that one. And now these two are the last ones. These are the ones I want, right? So the derivative of the loss with respect to the weight vector and the derivative of the loss with respect to b. And if I have computed these, then I can now just push that in to my gradient descent or my stochastic gradient descent. But you see, again, I did this sort of like in layers where I took the loss and I took the derivative with the thing that's sort of most immediately close to the loss, which is y. And then now I've backed away and I said, now that I've done that, I can kind of afford, if you will, to take the derivative with respect to the loss something kind of further away, like one sort of level further away, which is z. But to do that, it's easiest if I've computed the thing above. And so again, you see this structure. And this is going to be called the backward pass, because if you think of the loss as like like moving towards the loss, we think of as forward, and moving away from the loss as backwards. And so you'll hear, like I'll keep saying these so that they start to make sense to you. But so this is the kind of structure you see, and we're going to go through it more so it will become even clearer. But are there any questions so far? The slides are available. Is there a reason people are taking pictures? You want them like immediately? Is that why? I guess, I see, okay. Okay, so, right, so what is the structure here? I've just been saying it over and over, is that we're reusing things kind of from the previous line of math here. And we're gonna actually learn to draw diagrams that help us think about it in this structured way. Because right now, maybe it still looks a little funky to you if you haven't seen it very much before. And so the way these things have now become popularly thought about is in general as computation graphs. And actually, these are now used even outside of neural networks, but it's really neural networks that made these very popular, and the software developed such that you can readily do this in many areas of machine learning. But they kind of came, at least for machine learning, from neural networks. And so neural networks are going to help us to structure these computations such that we can readily code it. And so we're gonna, as I said, compute a loss, which is a forward pass. You're gonna take your inputs x, you're gonna have your parameters w and b, and from that and the functional form, you're gonna compute z, right, just like this. And then once you have z, you're gonna compute y. It's just a graphical picture. And in one of the homeworks, we're gonna have you draw one of these out. So I'm sort of also going through it because you should learn to think about it in this way, and then the loss. Okay, and so, great. And so now I'm gonna do, I'm gonna try and get you all the way to what, like an actual formula for backpropagation that you could actually code. Because we're not quite there yet, right? I've given you the intuition and the ideas, but if I said, okay, now go code this, you'd probably have to think quite a bit. So let's keep going with this. And to do that, we're gonna introduce a slightly unconventional notation, but I really like it, maybe because it's from my alma mater in Toronto. But so whenever you see a variable with a bar on top, what it means is that's the derivative of the loss with respect to that variable. So you're gonna have to remember that because we're gonna see that all over. And it's just sometimes we call this the error. And so sometimes people refer to backpropagation as passing around like these errors from sort of level to level, if you will. And so, and sometimes we also talk about these as messages. So we're passing the messages around. And that's sort of to distinguish it from like mathematical concepts of how you compute the derivative to practical software engineering considerations of how do you practically compute the gradient. So, okay, so if now all I'm doing is changing the notation here a little bit. And so now we have, well, computing the loss looks the same because that has no derivatives. And now computing the derivative, I'm just saying, I'm rewriting what I had on the previous slide in this new notation, right? So this is now the derivative of the loss with respect to y. This is the derivative of the loss with respect to z, which makes use of the derivative of the loss with respect to y, and so on and so forth. Okay, that's just a notational change to make things a little bit easier. Wow, I feel like a slide just went missing. Hang on. Oh no, that's good. Okay. Okay, so, and so far we just did the sort of regular chain rule, right? But that's not gonna work if we have more complicated loss functions. And so these are two examples where it's gonna break down and where you're gonna have to use the more generalized version, which is the multivariate chain rule. And so these are, in this case, what you have is regularized, like a ridge regression. So in ridge regression, of course, you know, you have the regular mean squared error. I don't have you guys gotta remind me when the laser pointer goes away. Okay. Maybe it's not useful, so you don't notice. But in any case, I like it. So, okay, you have the regular mean squared error, and then you have lambda, the ridge penalty times the loss. And if you draw it as a graph like this, then what you see now is that when you're going to be back propagating these derivatives, you're now, for w, you're going to have to get stuff through z and through r when you do back propagation. And so things are going to be a little bit more complicated. And in general, this is going to happen all over the place. And so we need to just remember or learn what the multivariate chain rule is. And so just, there's nothing complicated, right? It just says that if you have taking the derivative with respect to t, where you now have sort of two different things, as shown in the picture here, then you just kind of do, you use this rule here, right? You just basically do it for each of them, and then you add them together. There's a simple example here. So if you haven't seen this, like you can just go look at the slide, and there's nothing complicated about this. But this is just for these cases where parameters go through many variables, get used in many variables, which is, of course, definitely happens in a neural network. And so just, again, like the first time you see this, this might not be obvious, but I'll point it out. Maybe if you go look at the slides again, you think about it at home and you're doing the homework, you'll see this. But so in the course of that sort of procedure I've been slowly outlining, these things are the things that get reused, right, from the previous layer. So these are the things we kind of refer to as messages. We've already computed it, let's just grab it and use it. And then these are things that we have to evaluate kind of right now. And so that's just sometimes useful to think about. So, right, so now how do we actually do this full back propagation algorithm? I've been slowly trying to get you to think about how we can do this in a structured way and introduce some notation. So again, this is, we're gonna compute the loss. Again, that's the forward pass. But the way we're gonna think about this, again, as a computer scientist, so we can write some code to do this, is we're gonna first assign a topological ordering of the computation graph. And so that's important. If we don't have that, then we cannot programmatically compute the gradient in this way. So you need to know the graph, and you need to read off the topological ordering from that, right? So these guys come before this comes before this comes before that, and so on and so forth. And so now we're gonna, so the parents of W are Z, right? The parent of Z is Y. And so so what this says is for I equals 1 to n, and this is the forward pass. So we start at the beginning, and we compute VI as a function of its parents. So you compute its parents. Sorry, the parents of Z are these guys. I said it the wrong way around, right? And then we're gonna work our way forward. So first, in this loop here, we're gonna, these have no parents, right? So they just are what they are. And then for Z, we compute it as a function of these guys. And then Y, we compute it as a function of its parent Z. And then the loss, we compute as a function of its two parents here. So again, this is the same structure where I'm simply using stuff at the last layer. And of course, in the loss, I think it's super easy to see. It's when you start to do this backward pass for the derivative where it becomes much less intuitive, right? The forward pass, you can just see that this makes sense. The other one, you have to kind of believe the chain rule for. So then, as a sort of bookkeeping trick, so that we can write a general formula, we're now just going to start computing these backward messages, and which are going to be denoted V with a thing on top of it. And just again, as a bookkeeping trick, so we can write this formula generally, we're going to set the Vn to 1. And then when you work through this on your own, you can even just see it in one of these slides here. But and then what you're going to do again is just the same thing I was talking about, where you're taking information here and then you're passing it to here, and you can now compactly write this in this convenient form here, where and so this is sort of how you programmatically now can compute the gradient using backpropagation. And sorry, CH here is the children. I should add that to the slide, right? These are the parents, and these are the children. So in the forward pass, you need to know your parents, and in the backward pass, you need to know your children. Okay, so here's an example. Partly it's kind of fast to go through this in class, but it's mostly here just so you can take a look on your own. There's plenty of other examples on the web, but I think this is a very nice style of thinking and nice notation, and you can work this one through. And this one has one of these things here where if the W comes to Z and to R, and that's where you get this pink stuff here, right? This is where you get the multivariate chain rule, where you have to add these two things together. But it otherwise, so it just shows you how that fits in quite nicely. And then this is another one, and again, I don't think. Unless people want me to kind of go through line by line or give you a few minutes to think about it. Who wants me to go through this line by line? Who wants to just look at it at home? Let's see. Okay, well, I saw some people put up their hand. So let's just do it here again. So you can see. I'll kind of walk you through it slowly again. But then again, you have this topological ordering, and the forward passing, right? Again, it's sort of the same thing as you say. First, I compute from these have no parents, right? There's nothing up here, so they just are what they are. Then I go to the next variable Z, and I compute what it should be from its parents here, which are X, B, W, and Y. Same thing everywhere. The only difference now is that I have this R thing, right? This is like a partial order, of course. So I could compute R or L first. There's not any reason, right? So L only needs me to have computed Y, and R needs me to have computed W. So there is some leniency here on the order of these things because it's like a partial order. And then finally, I compute the final loss, which just adds these two things together. Okay, that's straightforward. And now this is this bookkeeping trick I said, where you just say that at the very last layer, you say the derivative with respect to it. Well, it is actually 1, right? So, and then you work your way back. So we saw in the forward pass, just to emphasize, we were going from down here to up here. In these computations, and so that's forward. And now in backward pass, we're starting up here, and we're going to go backwards. So now we have the derivative of R. The loss with respect to R is this guy, is going to be the thing from above, up there, this child, if you will, and then again, just use the chain rule. And then we can actually just look at what this is. This is just a lambda, right? We read it off from here. And now, and so again, we're just reusing. So this guy gets used here, and then this is just evaluating to that. And now we go one further, as we take the derivative of the loss with respect to this guy. That's this. And again, we grab the guy above, because that's what the sort of template said, and then we compute the rest we need for the chain rule, and so on and so forth. And it's just in this case, when we get to W, so W is now all the way down here, we have to grab stuff from here and from here. And again, that is just the multivariate chain rule. So you grab the thing from above and then the appropriate chain rule derivative. And similarly for the other part there. So you need to make sure you get both of those messages to get the correct gradient. And then that's, in this case, that's the only sort of thing that has this weird path. And then you keep going. And ultimately, you get now, well, these two things here, I mean, don't lose track of what we're trying to do, right? We're trying to get the derivative of the loss with respect to W, that's this guy, and the derivative of the loss with respect to B. And of course, in general, when you have these huge networks, you need to do that for every weight, every parameter in the whole network, but it's always gonna have this pattern, and that's the really cool thing about this, is you can programmatically do it, and it turns out also that it's like computationally very, very efficient. Okay, so I'll leave this particular example to you guys to do on your own, to take a look. And I'll just point out also, I'm not going to go into a lot of detail, but let's just say, is this the same example? Yeah, okay, so right, this is something called a multi-layer perceptron. I think it's in the notes. And to be clear, I found some confusion about whether does everyone here know you're not responsible for everything in the actual PDF notes? Like, you're responsible for what's in lecture, and those are meant to be auxiliary and supplemental. And so if you want to, I think, actually, I don't even know if it's in these notes, but in Professor Shushuk's version, that he does the multi-layer perceptron, and you can read about it there. But we're not going to kind of belabor that model. But in this case, right, all these little red things here, these are parameters that we want to take the gradient of, and each one is written, you can see it as these indices, right? So it's actually part of a vector, and each of these is a scalar. And so actually, in general, it's nicer if you can vectorize things if you're coding it right. And so this shows you how you can go from the previous page where you had like zi, h sub I, to get the whole vector z in one go, the whole h in one go. And so it's much sort of nicer to code things this way, and it could be more efficient computationally. Okay, so just to reiterate, back propagation is this algorithm for computing gradients, but the kind of neat thing is that it's like you can think of it as message passing, where you're being really efficient about caching information, right? So if you just did this sort of willy-nilly, like from like a pen and paper for calculus, you would be recomputing those terms, the same terms over and over, because you wouldn't have carefully structured it like this, where you get to exactly reuse things at the right time, right? The only reason we get to reuse it at the right time is that I said I'm going to pay attention to the topological order, and be very clever about how I do this. But it'd be pretty easy to just be computing the same partial derivatives over and over and to waste computational time. And so I guess that's the main, that's the gist of back propagation. Are there any questions? I'll say a bit more about it as well, but that's the main. I think until you sit down and do it yourself, that that's the best way to learn it, and that's why you'll do it in your home. Maybe you'll do it for fun tonight. Okay, so what is the computational cost of these things? So roughly when you do a forward pass, you're computing something that looks like this, plus there's like a non-linearity in there, but so it's roughly one add-multiply operation. And when you go backwards, you typically have to compute two things. And so it's sort of roughly twice as expensive to go back as to go forward. But the really, I think that's maybe not so interesting, but the thing that is interesting, right, is that this procedure is linear in the number of parameters, and it's linear in the number of inputs, and it's linear in the number of hidden nodes. And so that's pretty astonishing that we can, I think it's pretty impressive that we can compute the gradient with that. And so naively, if you were to, think of doing finite difference estimates of the gradient, where you're just using like the definition of derivatives, right, of like x plus delta x over delta x, you can always compute gradients numerically using that definition. If you do that and you sit down and write it out, you'll find this is sort of dramatically more expensive. So it's completely general and brain dead, but you would die on computation. Okay, so it's also sort of nice to think now about 3 different ways we can think about the gradient, and sometimes one is useful and sometimes another is useful, right? So we've seen it sort of drawn as we're doing gradient descent, and this is useful to just think about behavior of gradient descent and convergence and problems with the condition number of the Hessian. So this is like a really nice intuitive way that serves its purpose. And then we have just the chain rule, which is of course we know from calculus, and then we can couple that chain rule to thinking about computation graphs that enable us to do this in this sort of very nice programmatic way. And so, yeah, just keep that in mind, that sometimes different ways to think about things each serve their own purpose. Okay, so now that we've gone over backpropagation, I'm going to talk a little bit about the activation function. So far, I've just given you the machinery to compute gradients irrespective of what those activation functions are. And so you might remember I showed you these in the beginning. And so we have this linear threshold, and then just linear, sigmoid, hyperbolic, tangent. This is a thing that's typically applied at each node, unless you're the guy up there who doesn't like to use them. So the problem, what's the problem with this one? What, should we use these? Can we use these? What would go wrong?
Not differentiable.
It's non-differentiable. So yeah, that's right. You wouldn't get any gradient information because the gradient's 0 here, it's like undefined here, and it's 0 here. So you can use it, but good luck using gradient descent. You're not really going to have a good way to train the model. Certainly not using backpropagation. Right, so it's effectively 0 everywhere. Okay, so let's scrap that one. Although people did use those in the old days. There was this thing called the perceptron, and they did use this, and it didn't converge unless you had very clean data, clean in some technical sense that we're going to learn about in a couple of lectures. Okay, so linear. So what's the problem with the linear activation?
Useless.
It's what? Right, it's the thing I said before, is you can compose all these linear functions, and at the end of the day, you're going to have a linear function, and that's just going to be linear regression, so you're not going to get any benefit from all this beautiful machinery, and you won't be able to actually model things any better than you did with machine learning. Okay, what about these two? Not only is the gradient small, the gradient goes to 0. Both of these asymptote, yeah, it looks like on the picture that maybe they get small, but these actually, right, totally asymptote here, and similarly there. And so what that means is, as soon as you, remember these, you're piping in a linear additive thing into each of these, right? And so if that thing is really big or really small in either of these, you're also going to get 0 gradient. So this is better than linear threshold because it's not 0 everywhere, but it's only non-zero in this sort of special regime here. And so that can be really problematic. But for years, people, in fact, when I was in grad school, we only learned about sigmoidal units, and I don't think we coded them up or used them, but I can't remember. It's a long time ago. And yet it's better than linear because it is nonlinear, and therefore we get this sort of universal function approximator capacity out of it. Question?
We're going to be typing in like sigmoid stuff into these anyway, because that shouldn't be the range be like near the middle, so we don't worry about that.
So, right, we probably won't get there. So there's something called batch normalization, where what you do is, and you could use it with these, although it's usually used with something we're going to talk about in a second, is you augment it so that you can sort of, you shift it around in a systematic way to avoid this problem. So that is something that people commonly do, and it's called batch for batch normalization. And it's done in a, yeah, but intuitively it's what you just described, so that's nice thinking. Right, okay, so these are gonna get stuck. And you have to remember, like, why am I saying stuck, right? So if you get to, imagine you have a parameter that's W1, just some element of the wave vector, and it's going through this thing, and it has a 0 gradient. It means that it can never move, right? It's not just at that iteration, it's basically totally dead. You're totally stuck. So it's not just something bad at that iteration, it's bad forever. Okay, so what is the thing that people commonly use now? And this doesn't solve all the problems, but this is sort of the best compromise that people have found works well in practice. And so this is the thing I mentioned at the very beginning, this rectified linear unit. And it's just that if you're less than x, you get the value 0. And if you're greater, then you're linear. And so So where do we get a useful gradient? Here we get the useful gradient anywhere on the linear, and the gradient is just, of course, the slope, right? And down here we have the same problem again. But why might this be better than the sigmoid and the hyperbolic tangent, just intuitively? If I don't apply the trick that was just mentioned. Here basically I have a whole half of the real number line where the gradient's non-zero. Before I just had this tiny little bit. So basically you're much less likely. You can go arbitrarily large and you don't lose the gradient. You only lose the gradient if you go in this direction. So that's not a theoretical proof that they're better, but it's an intuition that of why they work better in practice. And so, all right, as I said, the things that have zero gradient that can never move again, these are, whether it's from a ReLU, from a sigmoid, or whatever, if the reason that they're not moving is because they've hit a zero gradient regime, then these are what we call dead units, and these have historically been a really big problem to deal with. And actually, the emergence of these is one of the reasons people struggled for a long time to get these models to work in practice. And so there are also some other tricks. So one, right, as I just mentioned, that was sort of suggested, was this thing called batch normalization. The other thing you can do is one intuitive way to think about it is that if you have really big gradients, things are going to jump around a lot more. And if they're really big, then you're more likely to jump into this sort of dead zone. And so you don't want the gradients to be too big. And so you can make this small, you can use a smaller learning rate. You can initialize things small. And then you can also, there's a whole cottage industry of making more general versions of ReLU that are so-called leaky. And what it means is you basically allow something in a parametric form to leak into here such that it's not technically zero. I was gonna put it in the slides, but actually no one really uses these. Like, you can read about them, but in practice, actually this is really the bread and butter of most applications nowadays, just these ReLUs with things like batch normalization, being careful how you initialize, and things like this. Okay, so why are these things good? Really, linear regression, we know that linear regression with arbitrarily high order polynomial features are also universal function approximators. And so why do these things dominate empirically? So it's not fully understood, but they certainly, you can get away essentially with fewer parameters than you would with the polynomial one because it's kind of learning its own features in a way. And that's again, not a proof, but and unfortunately for a lot of things, that's all you can really say with neural networks. And so it's not really fully understood why these things are so powerful. Again, people have some ideas, but again, it's an active area of research among theorists, and you see people from like theoretical physicists who are trying to explain this, from theoretical computer scientists, from all over the place, each with a completely different but interesting viewpoint that's shedding light on things. And so there's this great slide from a class at Stanford and it's quite funny because it's true. So what I just said is that the physicists see it in their way with like their spin glass models, and the theoretical machine learning people have their viewpoint. And this is a bit of a joke, which is to say that every theorist just looks at it in the mirror to see what they want, right? So you kind of think you understand it just because you're looking at it with your language and your machinery. And that's not to denigrate it. There's really interesting results there, but it is like a kind of really wide open field with just very, very different viewpoints. Okay, so that's the basics, but probably most of you have heard of other things that get used in practice, and so we won't necessarily have time to go into all of these, and certainly not today. I don't even have all the slides with me, but I have some of them with me. And so there's these things called convolutional neural networks, which involve pooling layers, and so that is what hopefully we'll get through today, at least partly. There's these very famous things actually that were first done at Microsoft, I think, in a competition called ResNet architecture. And so depending again how the class goes, I might be able to fit in a lecture about that. It's very, very interesting and very productive area of research right now, trying to understand these and why they work. And so this is another sort of interesting thing that happens in neural network is sometimes people just sort of hack these things as engineers, and then you get this like huge jump in improvement, and then people go try to understand this in a rigorous theoretical way. And so you get developments going in both directions, right? So sometimes people think these things through sort of very formally, rigorously, and then they do something that works quite well. But sometimes they're just like, man, I need this to work, and they just do crazy stuff, and then like the theory people go figure out why what they did actually worked. But as long as you're using these feed-forward neural networks, and you're only introducing differentiable components, then you can always apply this back propagation trick. So almost always, or everywhere, that's what people are actually using. So, okay, so that sort of closes the introduction of just sort of very vanilla, fully connected feed-forward neural networks. I just told you the sort of principles of how you can compute the gradients. And so now I'm going to talk a little bit about why would we want to do something different than a fully connected neural network, which is going to take us into these convolutional neural networks, which are very popular, although I should say they're very popular because they arose from the computer vision community. And again, this is a place where people just take these things and they apply them even when they don't necessarily make sense in the domain they're using. So as we're going through it, like think about what these convolutions are, and they're all kind of, all the intuition comes from images, and yet they're applied all over the place where it doesn't necessarily make sense. So, okay, that's his last lecture, but up until a moment ago, we talked about these fully connected layers. And so if there were this many inputs, and this many outputs at layer L, then we get sort of like, because it's fully connected, we just multiply these together, and that's how many parameters we get. So I mean, pretty obvious computation there, but just to motivate that this adds up really quickly. Like that is a lot of parameters. And even modern day, in the kinds of networks I'm gonna show you which can reduce this, even in those where you have reduced number of parameters, you still have millions of parameters in these networks. And in sort of old day statistics, right? Like no one had more than maybe 10. So this really kind of blows your mind if you come from classical statistics. So we know from the bias variance trade-off earlier in the class, right, that the variance scales roughly linearly in the number of parameters, and that variance is bad. And so in general, like, yeah, adding parameters is really good, but we don't necessarily want to just go crazy on that, because we want to reduce the bias. And so in some sense, you can think about different architectures sometimes, not always, but in terms of convolutions, is you could think of this as a way to reduce the number of parameters in a way that's domain specific for images, although can work well all over, without increasing, getting too much bias. And so in a sense, this is one way you can think of convolutional neural networks. So with fully connected layers, there's no notion that a feature is like reused, right? So imagine this is like an image here, then like these are somehow just computing each of different features. But I'm not computing like, you know, if you had an image of a cat, it's not like I'm looking for an edges in different places and reusing it. It's just everything has its own weight parameter. There's no weight sharing at all. And so just as an example, you could think about this where imagine you were doing, I know we haven't gone through classification, but let's just, I'm sure you can imagine what trying to classify a digit is, where you're trying to classify, is this image, is it a 1, 2, 3, all the way up to 0? And so these are the weight vectors in the neural network, in a fully connected neural network. And so right now it says iteration 1, and I'm gonna just hit the thing, it's gonna say 2, and as I click it, these are gonna change over training. And oops, okay, so as I get to iteration 7, you're gonna see that this weight vector is a huge template that basically, like, it just, you do this inner product essentially with the vectorized image and this weight vector, and it looks like a 1 if it's high, then that tells you if it's a 1, if you get a 2, a 3, and so each of these weight matrices is just an entire number, right? There's nothing kind of very local about it. It's just, nothing is shared. It's not decomposing the image in any way. It's just like, do you see a 1 on the image or not? And so like we see this sort of template matching, and it's very rigid, right? It's a bit brittle, and it's hard to get much complexity if you just do that, because you can't build things up from simpler features. You just have to say, this is a 2. And a 2, like, you know, that's just handwriting and a digit, but imagine you have something much more complex, then you're gonna have to just have a crazy number of parameters to do it. So, and the predicted class is essentially the template that matches best with no decomposition. And so what we'd really like is something that has parts and compositions that's like more compact and more robust than that. And so in some sense, this is another way that you can think of convolutional neural networks, is to have a sort of parts and a hierarchy of things. And so, right, you could imagine starting with some very simple features at the lowest level where you apply this like as a filter, but you apply it all over the image in different places, like, and it tells you, is there an edge there in this particular orientation? So each of these are roughly like edge detectors at some orientation. And so you can imagine that if you could detect edges at different orientations, all over the image, repeating them now, reusing them, and then you could somehow assemble them, then you could start to get richer representations with many fewer parameters. Okay, so so that's kind of all the intuition again, is you have this input image and you get these like low-level parts. Here these would be like edge detectors, and then mid-level parts where these have somehow been assembled through the next layer of the network to create, I mean, I'm not sure what they are, but these are clearly very simple. These you start to see some wheels and like a top of a car and stuff. And so you can imagine that you now get this sort of hierarchy of things that lets you classify things like a car or a bike and things like that. So, we want a neural network architecture that's gonna let us learn these sort of feature detectors, not a global template that you just slam on the whole image, but actually feature detectors that like sweep over the image, look for stuff, and then the outputs get combined together. And that's what convets are gonna let us do. And this is another example of like a hierarchy that emerges where you have these sort of edge detectors and you get sort of parts of faces, and then they get assembled into entire faces here in this hierarchical way. Okay, so how is this gonna work? So again, this is the fully connected layer where at some particular hidden layer, these are 3 hidden units, all the things feed into everything, right? There's no sparsity here at all. And this is some pictorial representation you can think about if that helps. And in contrast, what's going to happen with a convolutional network is we're going to get sort of locally connected layers where many of those things drop out. And instead, like this weight vector here is only going to be applied to a given part of the image, but it'll be applied repeatedly in the same manner all over the image. And what we're going to do is we're going to force the weights to be shared, which means essentially that this little template I scan all over, and it's always the same weights. So it's always doing the same feature detection all over the whole image. And the colors here are meant to show that that they're shared, even though they look like different weights. So, and this is kind of a nice pictorial representation. I think when you're thinking about convolutional networks, because they come from images, they make most sense for images. It's always like it's easiest to think that the input of the neural network is this square image. So that's supposed to be the thing down here. This big, or sorry, the blue square actually is the sort of input image, like maybe of a cat, and you're trying to decide is this a cat or is it a dog? And then what you do is you have these, what they call a filter bank. So each of these is like a little filter, and I say little because it's specifically smaller than the size of the whole image. In particular, it's this thing moving around here, right? It's the size, in this example schematic, it's 3 by 3, and this is this notion in which you now, instead of just throwing one template on the whole image, you're now scanning the image and say, how much of that feature do I see here? How much do I see here? How much do I see here? And then you do that for a whole bunch of different filters. And of course, we're going to learn these filters, right? So that's the other thing. I'm like, when I'm showing you, I'm assuming they have some value, and I'm showing you what a potentially sensible value that might emerge with them. And so once you do that, now you get the output layer here. And depending on some of the nuances, that output layer could be of a different size or not. We might slowly get to some of those or not. I wanted to at least just give you a bit of convolutional neural networks. It probably won't go into this more next week because we need to move on, but if there's time at the end, I'll finish this and go into some other things, probably in the last week. So, and then, so now the depth of you get an output volume because you have like what we call is like a filter bank. This is like a filter bank. And so each one of these things gets applied across the whole image in many, many locations, and then you do each of them. And so sometimes we think of this as like a sort of an output volume. And then of course, just as we do with regular neural networks, we can stack these things. And this gives us this, and what happens is, because, I mean, we hope that we get this hierarchical representation like what I showed you, but those examples actually, as far as I know, did emerge from training a neural network, and certainly that is what you see. And so it's kind of interesting, right? You say, I want this hierarchical thing, and it turns out if you set it up this way, this actually naturally emerges, right? No one's actually imposing that these are low-level features, these are mid-level features, and these are more complex features right before you make a prediction. That's just actually what emerges when you give it a ton of training data and you run gradient descent. So, so CNNs, you know, there's a couple. I don't work in these areas, but so in computer vision, there's a bunch of sort of benchmark competitions and things like this. And so, roughly in only 2012 did, I say only, but you probably think that's a long time ago. So that's when CNN started to actually win competitions. And before that, it was other models. And you can see actually with 8 layers at this point. So lower here is better. And then this is also 8 layers. You see you get to 19 and to 22 layers. Basically, no one ever got past 22 layers until a few years ago. And the only way they got past that was to use a different architecture. And there's some really interesting ideas there that we may have time to go into, but this is where the story of ResNets comes in, is why did no one ever train anything more than 22 layers? And how can you do that? Okay, so where are we on time? Okay, we still have a few minutes. Okay, so right, so intuitively, like, and I think I've already described this, but just to drive it home, is the this is actually technically, and we'll briefly at least today go through this. Like, this is like mathematically a convolution operation, and we'll see what that looks like. But what it really means intuitively is you're scanning this thing along, looking for, say, edges or for eyes or for whatever, and each part of the image. And sometimes in this example, you can, if you look at it, you'll see that it's actually skipping a position, right? It's not moving just 1 over. Sometimes it's actually hopping 2 over. And in the lingo of neural networks and in like the software packages you can use, this is called the stride. And so people can play around with the stride, and depending on the stride, the output will be smaller or bigger, and things like this. Okay, so what does convolution look like as a mathematical operator? Is there a class that people here learn this in? I'm curious. What's the class? 118. What is it called?
Signal
Fourier
function.
analysis and wavelets. I see. But like, so how many people here took that? Out of curiosity. What's that? Well, no, you're wrong. You're wrong. There's another guy.
Hey.
You guys know each other? What's his name? It's suspicious. You don't know his name. Okay. So, all right. So what I showed you were 2D convolutions, right? Because it's 2D because I had like a matrix going over a matrix, but it's easier to think first with what is a 1D convolution. And these come from signal processing, that I actually took a long time ago. I mostly forget, and you don't need to know all the ins and outs of how it arose, although you may want to. But so in the one-dimensional case, you have 2 vectors, A and B, and if you convolve them, it's just then the teeth element. So remember, A is some vector, B is some vector, and you want to know what the teeth element of the convolution is. Then you compute this form here. And so there's different ways to think about it, and actually it's much easier if I just show you pictorially. So this one is not natural for me, so there's a method 1 you see here, and there's a method 2, and you'll see they both compute the same thing. The end result is 2, 1, 4, minus 1, 2, and on the previous one it's this again, 2, 1, 4, minus 2. So this one, which I somehow don't like, because I like this idea of like moving the filter thing around. So in method 1, if you want to convolve A and B, you take, so this is A, this is B, and this symbol here is the convolution symbol. Then what you do is you translate and scale. So you take this thing, that's the second argument, and you move it. So here it's all the way to the left. Here you see it's been moved over once. Here it's been moved over twice. And then you multiply it by a scalar, and the scalar you multiply it by is, in this case, the first element, in this case, the second element, and in the third case, this element. Then you add these all up, and you get this. So it's not very intuitive, but at least visually you can see that that's one way to compute it. The second way, which is more like what I was showing you these little animations of, is flip and filter. So again, we want to convolve A and B here, and in this case, we're going to flip this guy around, and that sort of arises from where these things come from in signal processing, so don't worry too much about the flip if you don't like it. But so you take this, and you can see now this thing is not shifting as it was before. This just stays in the same position. And instead, you take this, you flip it, and you filter, and then you filter over here, and then you filter over here, and then you add these up. And so this is kind of like the one-dimensional version of the little animation I was showing you. You go here, 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 except there's a flip in it, basically. Was there a question? You just, like, that would just be a parameter like the stride. Like, so there's a couple of things. One is you need to know the stride, which is sort of how much you hop over. The other thing is you need to know what to do at the edges. So imagine you think of, let's see, you think of this thing as the image, let's say, and this is the feature detector. Then, like, right now, this thing is hanging off of the image, if you will, right? Because there's no image here. And so there's different ways you can deal with that. So in this case, I'm saying you can go all the way out, and what happens is when you hang over, I ignore you, right? Because basically this is a two, and then, but you could say, I refuse to compute it where there's a hanging out, and that will mean that my output is smaller as a result. Or you can also choose to mirror it such that it has no empty spots. So there's several decisions that I'm glossing over, and those you would just decide. And once they're decided, you would program it in a way where it does that, and then it shouldn't change anything about back propagation. It just, you have a slightly different sort of functional form, if you will. Okay, and you can also view it a third way, which is as a single matrix multiplication. So in this case, it's the same two vectors. I'm convolving this with this, and I've created this matrix where I've repeated what is essentially the filter, right? Or sorry, not the filter. This is what you should think of as the image in a way. So if this were the image, and this is one of those filters, you're going to apply it to each place in turn. And so this matrix actually has size 5 by 3. And so technically it has 15 entries, but it actually really only has 3 parameters, right? It's just 1, 1, 2. So there's some sort of like, there's a formal name for this, I forget it. Maybe it's the Toklets, I don't know, it was a long time ago. But so you've just repeated it. And just by virtue of sort of this special augmented matrix, you can now perform convolution as a matrix operation, although that's not necessarily the most efficient way to do it. So what are some of the properties of convolution? Commutativity, linearity, and now, linearity is nice because we're going to be doing gradients through them. But so then that gives you a sense of what happens in 1 dimension. 2 dimension isn't terribly different. It's just that everything is now a matrix instead of a vector. And so you get involved in the matrix A with the matrix B. This now directly relates to those little schematic animations that I was showing you. And so again, you can do the same thing where you can view this as a translate and scale. Again, I don't like this one as much. I like this one better. So in this case, this is like your big image. This is one of those filters. And this shows you basically that if I take the little filter here, this guy, and I apply it to this position, then I'll get this -4 here, just by that inner product. And you could work through it. And here, again, there's a decision to be made about what happens when it hangs over, right? So in this case, this is what I mean by hanging over, is the filters has 2 spots where there's no image, but I'm still computing a value there. And again, that's a user decision. You can say, I'm going to do that or I'm not. If you decide not to allow for that, then this last row won't exist, and the output matrix will be consequently smaller. Okay, so at the end we're going to learn these things, right? But there's a whole, you can take whole classes on image processing, and actually there are well-known filters that people actually just use to do image processing. And so, for example, this is kind of a known filter. Can anyone tell? And first of all, another question before I was going to ask you, does anyone know what this is going to do? Sort of just, could you describe in English, like what convolving this with that image will do? But before I do that, does anyone know who's in the picture? Jeff Hinton, very good, yeah. So he's one of the 3 Turing Award winners. He's sort of the granddaddy of neural networks. And so actually, when I did my PhD, he was there. At the time, he wasn't. I mean, he was still famous, but in fact, I once went to this machine learning conference, and I started talking to him like 5 years ago before he got the Turing Award, and within 3 minutes, there was about 100 people around us just listening, which is kind of crazy. But okay, so does anyone know if I convolve this particular filter with Jeff, what will it do to Jeff? Like, will it make him go bald? Any ideas? What? It'll look blurry. Yeah, this is basically a blurring filter. And you can think about that. Again, it's useful to, like, I'm doing this also so that when you go home and you look at this, you can think about, like, well, if I put this at any given point and I sort of, and if I flip this, right, this is symmetric. 2D, you flip it technically both ways, but it's symmetric, so then it won't do anything. And then you're basically, in a sense, you're doing a dot product of this thing at some particular part of the image. And so you're mostly taking the center pixel, but you're bleeding in a little bit of the things adjacent to it. And so, yeah, that gives you like a slight blurring. Can you even see it? They both look equally blurry here, don't they? Not on my screen. Do they? Can you tell?
Oh, yeah.
Oh, you can, okay. I see, from here they look both blurry. Okay, so here's another one. Can anyone tell what this one's doing?
Sleep.
What? Edge detection. Is it just obvious, or you've seen these? Oh, okay, then you can't talk. All right, this is edge detection, right? And so it's basically saying don't take anything from the middle, but see if there's a big difference between the stuff on the left and on the right. And in particular, it's vertical edge detection, right? Precisely because it's aligned in this way. And so what you get is now like all the highlights of where Jeff has edges. That makes him look especially bold. Okay, you're not allowed to talk. What's this one? Actually, this one's a bit, I don't, yeah, anyone? Who didn't take that class, the two people?
Sharpen?
Oh, you cheated. How'd you know?
Medium data science.
Very good. Okay, so yeah, this one is sharpening. And actually, frankly, I'm not sure I know the intuition of why that is. Do you know?
You enhance each central pixel and you bleed out the
Oh,
values.
yeah, that's,
increase contrast.
Yeah, that's true, Actually, yeah, that makes sense. Very good. Right, but just to emphasize, like, so you get this I'm trying to give you an intuition of what convolution can do. So it can be a template, but it can also do these other kinds of things that may be useful. Maybe for some reason it's helpful to blur before you pipe it up. But in general, of course, we're learning these. Like, that's the point of the neural networks, is that there's these compositions of convolutions that go through nonlinearities and where we learn these parameters. And so there's like a little bit more to say. Well, we have 3 more minutes. Okay, I'll finish and see where we end up. But so, right, just always keep in mind that we're looking at these things very intuitively, but at the end of the day, we're learning these. And then you can go back and ask afterwards, like, what are they actually doing, if you can tell. But, and so this is related to the comment I made before, is like, what is the size of the output layer? And so that, well, of course that depends on the image size here, which is shown to be 4 by 4. It depends on how many filters you have and what the size of the filter is. And it depends on the stride, which is whether you skip any pixels or not. And it also depends on whether you choose to do that. What I said is, or do you let it hang off? The word I should have said was zero padding. I think I just forgot it. And so, but in any case, if you have these things and you have a stride of 1, then the output from the filter has this size, which in this case, for these numbers, is 2 by 2. So again, you can go look at this after and just think it through. And of course, if you change any of these things, you change the output size as well. And so what's the time complexity here? So we know that the output from one filter has this size, if we have a stride of 1. And so for each one of those outputs in this green thing here, we have to do this convolution, which basically is an operation that is k-squared, right? It's like the size of the filter, because you're kind of doing this like dot product with it. So that takes k-squared times that. And so if you have n filters, then you then just multiply that by n. And so, right, we're not going to have time, but I'll just say really quickly that so far what I talked about are these convolutional layers, but there's also something else called pooling layers. And so first you typically apply a convolution, and you get these outputs in this like output volume that like has some depth depending on how big your filter bank is. And then you're going to do pooling. And I'm going to skip ahead to a slide just to try to explain that here. Right, so this is what you might think. So pooling is some way to reduce that final output volume in some way. And one way you'll frequently hear is max pooling. So what is the idea of max pooling is, imagine that I have this, in this case, like an eye detector. So the filter, it so happens at this point in gradient descent, or after I've trained it, or let's say after I trained it, it's an eye detector, one of the filters, right? So when I scan it everywhere, I say how much eye is there, do I think there is here, how much do I think there is here, and I do it everywhere, so that's what this is meant to depict. But now imagine that I'm trying to, the final goal is to say, is there a human in the image? Then I might, or maybe like better is like, is there a human with one eye? Then I only want to know really like, what's the best match to the eye? Like some of these might be very noisy or something. So I might just want to know what is the best match. And so I might take the output and say, give me the max of that. So that's what max pooling is. Or you might just do it within a small region or something like this. And so, right, we're out of time right now, but we may get to more of this. Anyway, there you go.